Hi, everyone. Welcome back. Thanks for coming back for the second half of the day where we're going to talk about scientific data. My name is Julie Sweetkind-Singer, and I'm the Assistant Director of Cartographic, Geospatial, and Scientific Data and Services here at Stanford. And I also work for Bob, so there you go. I'd like to first start off today with Jamie Kinney, who's the Principal Solutions Architect for Amazon Web Services. Take it away.
Thank you very much. So I work for Amazon Web Services, which, how many folks are familiar with AWS and the cloud computing portion business at Amazon? That's great to see. I manage a team of solution architects, individuals that work very closely with customers to help them match Amazon and third-party technologies and solutions to their needs, focusing specifically on the scientific and research community. So we work very closely with space agencies, Department of Energy labs, universities around the world. And I want to thank you for the opportunity to present today. I'm going to spend about 25 minutes and leave a little bit of time for questions afterwards, providing just a little bit of an introduction to two of our services, and then really focus on one specific example of an executable paper concept from the National Institute of Mental Health National Database for Autism Research. And so briefly, just talking about Amazon Web Services, you've probably seen this statistic before. Every single day, Amazon is provisioning enough infrastructure for our cloud business to power Amazon.com circa 2005. Actually 2003 in the screen, I think it's actually 2005 now. It's a very rapidly growing portion of our business. We operate data centers all over the world, including a region that's designed to host sensitive government workloads with the ITAR controls in place, primarily for the aerospace customers. And we offer a pretty broad range of services, including compute, network, storage, database technologies, as well as workflow deployment, monitoring, and other capabilities. And on top of this rich, globally accessible, internet-connected set of services, it's really possible to develop any type of solution, really. And so I wanted to dive into just two of these services to provide context before I really talk about the ENDAR example today. The first service I wanted to discuss is Amazon S3, or Amazon Simple Storage Services. So S3 is our object storage for online storage. And so we're currently managing over 2 trillion objects within Amazon S3, over 1 million requests per second against this globally accessible service. Anything that you write to S3 automatically replicated across multiple data centers. And the types of objects that you might write to S3 could be anything from tiles for a GIS application. It could be genomic information. It could be raw radar imagery. It could be XML or pictures that you want to back up from your home computer. A very, very popular service and one that's able to be treated as a massively distributed replicated file system. So if you're using a Hadoop application, as an alternative to HDFS, one could easily use S3 as the shared file system across one or many clusters that are concurrently connected to S3. And so with S3, you can access this storage through a web interface. Here we see just a listing of the OpenFMRI dataset that we host as a public dataset on AWS, as well as some of the individual objects that reside within that bucket. You can access from a command line interface if you prefer. There's open source tools, S3 Command being one of those. And then we have another service that ties into the solution I wanted to discuss today, which is the Amazon Elastic Compute Cloud. This is one of the most popular services we have. It's virtual servers that you can rent on an hourly basis. You pay as you go. One server running for 100 hours is just as expensive as 100 servers running for 1 hour. So for embarrassingly parallel applications, it's a fantastic tool to have in your belt. Offer a pretty broad range of instance types, including machines that have a 1/4 terabyte of memory SSDs or even little burst capacity machines for small departmental websites. We also have command line interfaces to EC2. Have a web console, makes it easy to administer, launch a 100-node cluster if you like. And probably most importantly, and this is the point I really want to emphasize, you have programmatic access to the Elastic Compute Cloud and any other service that we offer. So if you'd like to code in Python, for example, you can, within a script that's performing some statistical analysis, you can very easily provision a private network between Stanford and the Amazon cloud. You can launch machines. You can specify the machine image that those are derived from, either scientific Linux or the operating system of your choice, potentially with software that's pre-installed, and you can launch one or thousands of those machines, all within the favorite programming language that you use on a daily basis. And so how is this being used for scientific computing applications? The display that we see here, it's maybe a little bit hard to see in this room, is a map of the global scientific collaborations between 2005 and 2009. And I think this is the area where the cloud will really have a transformative impact on the way that science is conducted. So I work really closely with NASA. I've spent time working at JPL over the past 4 years. And what we see here are well, not all of the institutions, but many of the institutions that have worked on various instruments or aspects of the Mars Science Laboratory. And so you see lots of NASA centers, you'll see lots of universities, other space agencies around the world. And if you think about how a mission like MSL would have been conducted, how collaboration would occur prior to the advent of the cloud, you have scientists that are working together. The very first thing they have to do when they want to work on an instrument that's been proposed is figure out where they're going to store their data and how they're going to talk to each other's networks, and which operating systems to run, how to install software in a way that allows you to reproduce the work at one facility that's also being conducted at another facility. And that's hard with 2 institutions, but what happens when you have 20 institutions in that model? There's a lot of work that's involved just in managing the storage and the servers and the images and security policies and figuring out who can work where. And so the cloud provides a global infrastructure, a neutral environment in which you can create secure environments or open environments or something in between, if you like, where you can create collaborative databases, machine images, have effectively limitless compute and storage for the project, define security groups that allow specific individuals to have more privileges than others as appropriate. And the net effect of that is that instead of having to create many replicas of all the data and manage all of these variable environments, you simply create one shared environment, and then everybody accesses that regardless of where they're connecting from, with the rich permissions, of course, that you would expect to have. And before I go into the example of the National Database for Autism Research, I wanted to talk about one of 2 programs at Amazon that I'll mention today. The first is the Public Datasets program. So I'm one of the 2 people at Amazon who administers the Public Datasets initiative. This launched back in the 2009 timeframe, I believe, initially as a technology demonstration when we supported persistent storage in the form of elastic block storage for our virtual machines. We had a couple of sample data sets that you could instantiate just to show how you would instantiate a snapshot of your data back onto a running instance. Where we're going with the program now is we're hosting the gold standard reference data sets that we think will be useful to the scientific community. And we really have 2 goals in place. The first is very altruistic. We want to fundamentally accelerate the pace of scientific discovery, and we want to make it as easy as possible for researchers, for citizen scientists to not only do the work that they're doing today in the cloud, but for others to learn about these fields and hopefully become practitioners themselves. And then more selfishly, we believe that by hosting these data sets, we can achieve cost recovery by attracting additional data sets and by attracting the compute jobs that go hand in hand with these data sets if they're easy to use. And so if we look at the program today, we're hosting many data sets, including 1,000 genomes, common crawl corpus, many other relevant data sets that you might access on a regular basis. And what we're hoping to add over the next 6 months are machine images, workflows for MapReduce jobs, reference documentation that makes it very easy to reproduce work that was done to collect that data and then extend that work at other institutions. So one great example of how this model is being employed is illustrated with the National Database for Autism Research. So any researcher that's receiving funding from the National Institute for Mental Health and working with autism research will need to publish their data. And the way that they do that is through the National Database for Autism Research, which is hosted on the Amazon cloud, using S3 for all of the large object storage, using Amazon's relational database service to manage the relational metadata that's associated with everything that's written to the S3 object store. And then there's a rich web interface that you can use to query the data and find the papers, the labs, the data sets that might be of interest to you so that you can either review or reproduce or extend the work that's been done by another autism researcher. And where they're going with this now, and they've launched and announced this at the Organization for Human Brain Mapping conference that was in Seattle a week ago. They now have a site that they make available so that you can very easily instantiate your own relational database that has the data that you care about, has the references to the rich repository of large objects that are stored in Amazon S3, managed by the National Database for Autism Research. You can now easily create your own snapshot of that data in the cloud so that you can do this further research in an environment where you have the effectively limitless compute that an organization like Amazon Web Services provides. And you can get access to the snapshot within literally a minute or two, as opposed to the historical model of shipping large amounts of data, potentially hundreds of terabytes of data, back and forth between institutions. And so what we see here is the web interface for ENDAR that shows how you might query data from an individual laboratory, showing the experiments that were conducted, the data structures associated with a given laboratory, as well as links to download the data that was collected by that funded project. If you publish a paper as a result of your work, they also have the ability through these orange ovals that you see on the screen to very easily identify the data set that was associated with that journal submission so that you can quickly get a snapshot of that data, along with a reference to the journal article itself. So it's a very rich metadata structure and an easy way of distributing data that was perhaps harder to reach before the cloud came around. And so with this model, some very interesting things are possible. So just illustrating kind of the current model today. So if you have ENDAR's data sets that are hosted within the cloud context, using S3 to store hundreds of terabytes of genomic information, of observational information that's associated with given experiments, and then RDS being the database that's managing all the metadata, any researcher who wants access to that data would need to first query through the web interface, say these are the data sets of interest, and then download over a course of hours or days, perhaps longer, to get access to that. The net effect is that you see massive amounts of redundancy in the data that's being copied. It's very difficult to manage, it's very wasteful, very inefficient. And this is not how National Institute for Mental Health wants to use their funding. They want to fund new research instead. And so the cloud model instead has you instantiate very lightweight, on the order of magnitude of dollars per month, relational databases that have just that subset of metadata that's of interest to each researcher who's accessing this public data set. And so having the data accessible in the cloud not only offers some opportunities to increase efficiency, it also gives you access to a rich set of libraries and tools. Just a few of these are listed here. Galaxy is a fantastic genomics pipeline toolkit that's published on AWS and also available to run in your own data centers if you prefer. Nitric is a neuroscience, neuroimaging resource that you can launch as an Amazon machine image if you want to do brain visualizations in the cloud. Cloud BioLinux is a pre-configured Linux distribution that has a number of Python and other tools that are configured for genomic sequencing workloads. This is just a very, very small sampling. There are hundreds of these that are published on Amazon and on other clouds. And so having these resources available along with the data and making it very easy to access just the subset of data that's of interest to a given researcher really speeds up the time to science, which is of tremendous value. And so the model that we think is really interesting is that a researcher can now conduct an experiment, and as is happening with autism research, that data is now uploaded into the cloud. So this has been happening for a while now. And so where this really starts to get interesting now is that the review committee can easily reproduce those results. You have access to the data, you have access to machine images that have the same tools installed in exactly the same way that were used when that experiment was being conducted. So you don't have to waste time installing operating systems, installing libraries, installing tools, debugging these issues. Instead, you're focusing on validating the results and thinking about the techniques that were used. And then the results, once they're reviewed, are published in a peer-reviewed journal, including references, most importantly, to the data and to the machine images and other resources. In the case of the NDAR data, they're actually generating DOIs to reference these data sets. And now this is where I think it gets really interesting. When you have your experimental techniques that are documented in the journal article, you have your data that's being published, you have the tools, most importantly, associated with that data also running in the cloud. Now you have the ability, as new data sets come online from other very similar experiments also being published to the cloud, you can now, through automated workflows, rerun those experiments, but with new data sets. And with machine learning techniques, other capabilities that are now becoming more and more common across a wide array of scientific domains, it's now possible to to automate experimentation and come up with new observations that might not have been, new experiments that wouldn't have been run previously, or come up to new conclusions we might have missed without the ability to run these in a resource like the cloud that Amazon provides. And so this will, of course, there are some examples of these that are happening today. Elsevier has some really interesting work that's happening now in the form of the executable paper. There are teams at Stanford that are working on this. I think this is a field that's going to really be taking off in the next couple of years. And we hope that the cloud can play some role in accelerating the pace of these types of efforts. Finally, before I answer a couple of questions, I wanted to just also mention the AWS Education and Research Grants Program. So every year we give out millions of dollars in AWS credits to researchers around the world who are developing either innovative applications of the cloud, developing models like the executable papers that we described, or are creating new data sets that they want to make publicly available to other researchers around the world. So if you have an idea, if you know somebody that might be interested in this, encourage you to take a look at aws.amazon.com/grants and apply for these. We review these on a quarterly basis. If you have something that you think is of interest, we even have opportunities to accelerate those too. So please don't hesitate to reach out to us directly. My email is jkinney@amazon.com. So with that, I'd like to conclude and see if there's any questions that you might have.
All right. Thanks. You talk fast today. Questions?
So what happens in 30 years with your virtual machine image?
Yeah, that's a great question, and I'm not surprised to get that question in a room that has a few librarians in it. NASA's also concerned about this too. They have data, radar observations of near-Earth asteroids, and they want to make sure that as they get better techniques for finding these asteroids that might one day smash into Earth, and we develop better techniques for avoiding those, that they can ensure that data will always be around. So machine images, data formats are very important in figuring out a way to ensure access and ability to not only to retrieve those, but be able to access those over time is important. So we offer full Linux and Windows machine images. So it's a full Linux or Windows operating system. So the software that you're installing on Amazon Web Services, you could very easily install on-premise. In some cases, if you're importing a machine image from on-premise, you can very easily export that same machine image or derivatives of it back off-premise with a single API call from Amazon. But it's very easy to move not only your software installations that are running in the cloud back on-premise or to another location, but similarly, we offer APIs for shipping Amazon a drive, having us load your data and ship that via SneakerNet or over the internet back to another location if you like. So there's ways to avoid concerns around a lock-in or being tied too closely to one vendor and the success of that vendor in the long term. We also encourage you to look at kind of the standard contracts that are provided by cloud providers like Amazon that give you some period of notification to ensure that you're going to have time to react if a service that you're using is going offline. And so with our kind of the open way that you interact with operating systems, with APIs for quickly loading your data in and out of the cloud, and standard contractual terms, we feel our customers have some protection against that specific concern.
So I'll just start by saying I've benefited from your research support, and so thank you. one of the things I've noticed about grant agencies is that they like to give you money for resources, right? Technology resources. And then when the grant goes away, you have the computer. And so how would a researcher who was going to use the Amazon cloud resources in the way you suggest plan for sustainability in that environment?
That's a fantastic question. So we look at that very closely when we're considering grant applications. And so in some cases, we choose to fund data sets in perpetuity. We don't have a contract in place that describes that relationship, and perhaps we should. It's something we're taking a much closer look at. In some cases, though, we actually encourage the applicant for a grant to propose a model for sustainability. So we'll be happy to fund perhaps, say, the first 12 to 18 months of hosting of a given data set in the cloud. And by that point, hopefully you can demonstrate the value of that data set to a broader community, including those agencies that might fund it on an ongoing basis that are really designed and set up for that type of support to take it over from Amazon. At least in terms of providing the funding for it. But we're also looking at models. So today we have a marketplace in which you can host machine images. So you have an open source tool or commercial software that you want to make available to others. You can not only list it and make it accessible, in some cases you can price it above what we charge for the base infrastructure. And we're considering ways in which we might do the same thing with data sets that are not open data, but are more private data. And the implications of that, though, need to be weighed fairly heavily because we are very interested in keeping data as open as possible. But looking at any suggestions, and if there are folks in the room that have ideas on how we might take on cost recovery for these data sets so that we can host as many as possible, we'd certainly be receptive to those ideas.
Thank you very much, Jamie, and we'll move forward from here. Thanks.
Yeah.